Today we're going to talk about how to model and optimize a glass fiber reinforced tensile bar. For this project we used a transversely isotropic material model to see if we could accurately predict the deformation of a tensile bar. We also tried some optimization of the fiber orientation to see if we could hit a desired displacement. So why do we care about fiber orientation? Well, if you inject your tensile bar here, the plastic is going to flow along this direction. The glass fiber is going to freeze along this radius and it's going to stay in this orientation. This orientation is going to play a huge role in increasing the stiffness of your part, as you can see with this drawing down here. These glass fibers are oriented axially, but they're very, very weak in the cross flow direction. So for our modeling, we chose to just look at the upper right hand corner of our tensile bar. We used 34 bilinear plane stress quadrilateral elements with 2x2 Gaussian integration. We used symmetry boundary conditions for the bottom and left hand side where they were fixed in the Y and X direction respectively. And we applied 100 newtons per node over 9 nodes in the positive X direction to simulate a tensile test pull. This gave us the correct displacement field in the X direction. The material we chose to look at was a 45% glass-filled polypropylene, which is very, very common in the automotive industry. This material is very strong in the glass fiber direction but very weak in the cross flow. The tensile bar was also assumed to have a 1 mm thickness. Now for an isotropic model, you'd typically use this compliance matrix to model your tensile bar, but in our cases we're going to have to do something different. Because we want a different fiber orientation, we have to use this lamina material law, where we're going to input our orientation tensor and it's going to spit out a new D matrix. Of course, we got to invert this to get our stiffness matrix. For those of you that are still awake, what we did was we input a degree of orientation for the fiber for each element, we ran the function, and got a new D matrix. So let's try it for one orientation. As a benchmark, we modeled the exact same thing in Abacus using the same mesh, orientations, loading, and boundary conditions. What we found was, after summing the displacements multiplied by the force applied for each node, our error against Abacus was almost zero for all cases. So we went ahead and tried to make things a bit more complicated and used 3 sections of different orientations: 0, 45, and 90. Again, we measured ourselves against Abacus and we were almost zero. Because things were going so well, we tried 34 sections, different orientation. In a sense, each element is going to have a different orientation. Element 1 is going to have 0 degrees, element 2, 1 degree, and so on. This is done through an array, which gets plugged into our original function that we showed earlier. Again, that we found our error was almost close to 0 against Abacus. In addition, we tried a biquadratic evaluation versus Abacus. We tried just 45 degrees and found that our error was 0.85%. We think this error is higher due to the differences in integration between Abacus and ourselves. We also tried some optimization. What we asked was, what orientations would I need to achieve a specific displacement? Because saying 0 degrees is too easy to minimize the displacement, we chose to say we wanted a maximum deflection of 2.3 millimeters. What 3 different orientations will we need to find? We also used a faster CST mesh to improve our speed, because we knew it was going to take a lot of runs for it to converge. We used the optimization toolbox on MATLAB to find our 3 angles and to minimize our objective. After 146 runs, our optimization showed that to achieve the 2.3 millimeters of displacement, we needed 55.3 degrees, 17 degrees, and 88 degrees. Overall, we feel this project was a great success. We think that our bilinear quadratic model is very accurate. When modeling the transversely isotropic material model, each element can be modeled differently and still achieve accurate displacements. Also, optimization can be used to find the right fiber orientation and is also very accurate.